welcome to this Maths Made Easy video on trig graphs. And to start with, let's just quickly remind ourselves about our three trigonometric functions and their respective graphs. And to start with, we have our first graph here, which represents y equals sine x. So this is y equals sine x, and there's a few things we can deduce about our trigonometric function using this graph. We notice y equals sine x starts at the origin here. We notice we have a maximum of 1, and we can actually see that this repeats several times. We have a maximum here again at 1, and another maximum here again at 1. We also have a minimum of -1, and again we can see that repeats several times. And the reason that this repeats here is because what we say is that sine x is periodic about 360 degrees or 2 pi radians. So this is periodic about 360 degrees or 2 pi radians. And again, you can see that from the graph. Notice here at the origin, we're at 0, we're at the origin, and then after 360 degrees, we're back here. Okay, same again here at 720, and again here at -360. And again, you can see here when we're at our maximum at 1, this is when it's 90 degrees, and if you add 360 to 90, again you see the maximum here at 450. Okay, so that covers y equals sine x. So now what about y equals cos x? And again here we can see a few things from our graph. So let's note the function first. This is y equals cos x. And again we can see here for y equals cos x that we start at 1, and we have again a maximum of 1 here, which we can see again repeats several times, and we have a minimum of -1, and again this repeats several times. And again this repeats several times because y equals cos x is also periodic, and again exactly like sine x about 360 degrees or 2 pi radians. So that's everything we need to be concerned there with cos x. And finally, we move on to our final function here, which is y equals tan x. And you might notice that y equals tan x has quite an unusual shape, especially compared to our previous two trig functions. However, again, we can deduce several things from our graph here about y equals tan x. And again, we can see using the graph here that tan x is periodic. And be slightly careful here. Unlike the other two, it's not periodic about 360 degrees, but periodic about 180 degrees. Okay. And again, we can write that in radians as pi radians there. Okay. And again, you can see that clearly from your graph here. We start at the origin here. Well, if we add 180 degrees to that, we arrive here again. And you can see that again at -180. So we can make several comments here just to summarise here our three trig functions. For sine x, well, for sine x here, we can write this as sine x is equal to sine of x plus 360 degrees. So x plus 360 degrees. And again, we could write that as sine x, or sine of x minus 360 degrees. So sine of x minus 360 degrees there. Okay, we can repeat this again for cos, and cos follows in the exact same manner here. So cos here, cos x is going to be equal to exactly in the same case here, because it's periodic about the same number of degrees. So we can write that as cos of x plus 360 degrees, and this is equal to cos of x minus 360 degrees there. Okay. And finally, for tan x then, again, we can write this in a similar format. So we can write this as tan x here. And in this case, rather than it being x plus 360 degrees and x minus 360 degrees, as it's periodic about 180 degrees, then it's going to be tan of x plus 180 degrees, which is going to be equal to tan of x minus 180 degrees there. Okay. So that's our quick reminder there regarding our three trigonometric functions and their respective graphs. Moving on now to vertical translations here for trig graphs. And what we'll do here to start with is take a look at this blue curve. This is what we originally start with, and this blue curve represents y equals sine x. So this is y equals sine x. So I'll give you a quick moment here now just to think about what these two other curves represent. We have this green curve here, and we have this red curve, and these are both vertical translations. So hopefully you managed to gain an idea of what these translations might represent, or how we would denote these translations. Well, if we take a look at the green one here, in this case, if we start with our original blue one and compare this now with the green curve, what we can notice clearly is that this is an increase of 1 unit in the positive sense, in the positive direction. So this is a vertical increase of 1 unit, and we can clearly see this if you consider a few points here. It maps up 1 like that. Same again here, from the maximum here, it matches up there like that. So this is an increase of 1 unit in the vertical direction. So how would we denote that? Well, we simply write this as y equals sine x, and we add 1 unit to this. So this is plus 1, like so. And if we consider the red curve here now, and again let's just change our pen colour here. Well, in this case, again taking a look at our original graph and comparing this now to our red curve here, again if we start here for our blue curve and we go down like this, we can see this is a decrease of 1 unit. So in that case, we'd write this as y equals sine x, in this case now, minus 1. Everything's shifted down 1 unit there. So that gives us our 3 solutions there, or our 2 solutions there, for our 2 vertical translations. Moving on now to take a look at horizontal translations. And what we've been given here is our original curve of y equals sine x. So let's just denote that in blue here. And what we've got is we've got a new curve that's obtained through a horizontal translation here. So I'll give you a moment just to think about how this new curve is deduced using a horizontal translation. So hopefully you might have been able to figure out what this translation is, or what we have to do here to obtain it. Well, in this case, what we've got here is our green curve, which is a horizontal translation based on the blue curve, which our blue curve represents y equals sine x. So here, the way to think about this, if we start with a general point here, let's say the origin, let's take a look at what happens here. Now, if you notice, this is 90 degrees to the left, okay? Well, in that case, as this is 90 degrees to the left of our origin here, this is a horizontal translation to the left of where we started here. And the way we actually deduce that and write this translation, and this can cause issues, so we have to be slightly careful here. Think about it as in terms of the opposite here. So we're going 90 degrees to the left, however, we denote this as x plus 90 degrees here. Okay? And this can cause issues, so try not to get confused with this notation. Now we can write this in its general form here. If we just take a general example here, let's say y equals sine of x plus c. Okay, this is a translation to the left of c. Okay, so translation to the left of c. Okay, so what about, for example, sine? So y equals sine of x minus 45 degrees. Well, in this case, again, we think about this in terms of the opposite sign. So as this is minus 45 degrees, this is actually a translation of 45 degrees to the right. The misconception here is that this is 45 degrees to the left. However, in this case, this is a translation of 45 degrees to the right. Okay. So that concludes everything we need to be aware of there in regards to horizontal translation. Moving on now to vertical stretching here. And what we've got again is our original curve in dark blue here of y equals sine x. And what we'll do is we'll just note that down here. So this is y equals sine x in our dark blue. And using vertical stretching, we obtain 3 new curves. We have this purple colour curve, we have this green curve here, and we have this dark red curve. So I'll give you a moment just to think about these three curves and what we have to do to deduce those three curves using vertical stretching. Now hopefully you might have got somewhere with these three curves. Let's just take a brief look at these now. Now if we start with the green curve here, again it's going to start y equals, and what we need to do is just take a look at maybe a couple of points here. Well, for example, if we take this point here, which has a height of 1, that's our maximum point there for a sine x curve. Well, in that case here, what we need to do is think about the point underneath when we're comparing it to our green curve. Well, this point here is exactly halfway between our original curve and the x-axis. So in that case, this has a height of a half. So what that would suggest here is that we have a stretch of a half here. Okay. And again, you can also deduce that here by using our minimum point, this -1. Well, notice this is minus a half here, and again, that verifies our facts here that we have a vertical stretch of 1/2. So therefore, we write our equation as a half of sine x. Now that gives us our green curve. What about our purple curve here? And again, we just need to take a look at our original sine x graph and then our new curve here. Well, for our new curve, again, if we take this point here with a height of 1 and compare it now to this height here, which has a height of 2, what that would suggest then is that this is an increase or a vertical stretch here of 2. And again, we can also verify that here using our minimum point of -1, comparing it to our purple curve here of -2. And again, that verifies our idea here of a vertical stretch of 2. So we write that here as y equals 2 sine x. And now finally, moving on to this red curve here, this one's going to look a little bit different to the previous three curves here. But in this case, if we just think about this, again, if we start with our general point here, or our particular point here of a height of 1, and compare it now to our red curve here, notice this has a height of -1. And similarly, if we take this point here of -1 for our blue curve of y equals sine x, the red curve here, the dark red, has a height of 1. So what we notice here is we have a vertical stretch of -1 here. And when we write this as an equation, we don't write -1 sine x, we just write minus sine x there. Okay. And what that gives us then is the four equations that we can see that plots the respective curves here. Moving on now to horizontal stretching. And again, here what we start with is our blue curve, which represents y equals sine x. And again, let's just denote that here. So we have y equals sine x. And again, we obtain some new curves here using horizontal stretching. And again, I'll give you a brief moment here just to think about what the equations might be, representing the green, the purple, and the dark red curve here. So hopefully you might have got there with these equations. Let's take a look now first at our green equation. And here, again, it's going to start y equals, and what we can take a look at is our maximum point here. Okay, so we notice this corresponds to 90 degrees. But what about the maximum on our green curve? Well, that occurs there at 180 degrees. Well, what that suggests is that we've doubled the number of degrees. 90 degrees times 2 gives us 180 degrees. Well, in this case, as we write this now as a horizontal stretch, again we have to be slightly careful here. So this is going to be equal to sine. And the misconception here is that this would be 2x. However, we have to be slightly careful. We write this as a half x. Okay, so that represents our green curve there. Similarly, we can repeat this here for our dark red curve. Writing this in dark red then, we have y equals. And notice here now, similar to what we had here with the vertical stretching, we've essentially got a mirror image here. So in this case, we simply just write this as sine of minus x, or you can prefer to write that in a bracket to avoid any confusion there. Sine of minus x. And then finally here, and if we note this one here in purple for our purple curve here, well, again, using this example here of our maximum point corresponding to 90 degrees, well, if we look at our maximum point here, this is 45 degrees. So essentially what we've done is we've divided 90 by 2. Again, we have to be slightly careful here. We don't write this as sine a half x like we did for the green one, because notice that doubled it. So in that case, we do write this one as sine 2x then. And that corresponds to our purple curve there. And finally, we can conclude everything we have discovered so far regarding trig graphs and their transformations using this nice table here. And what we can see using this table, for example, if we are multiplying by n, and this is acting on x, then this is a horizontal stretch with a scale factor of 1 over n. Similarly, if we have a plus c term added on, and this is acting on x, then this is a horizontal translation c units to the left there. Okay, so this is where everyone kind of accidentally gets tripped up here. The mistake is usually to write this as c units to the right, as we're plus c, so you just have to be slightly careful there. Again, if we are multiplying by n and it's acting on the function of x, then that's a vertical stretch with a scale factor of n. And finally, if we have a plus c term added on, and we're acting on the function of x, then this is a vertical translation c units up. Okay. So this table is a really nice way of summarizing everything we've discovered so far with translations and transformations. Be sure to use this table wisely when working on problems of this type. And that concludes this Maths Made Easy video on trig graphs.